नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE and NEET. This video is regarding molecular orbital theory. This is the first episode in which we have discussed about the difference between molecular orbital theory and valence bond theory. Along with that, we have discussed how the wave function changes its sign with theta and phi in order to understand constructive and destructive overlapping of atomic orbitals. Valence bond theory was the first quantum mechanical theory of bonding, followed by molecular orbital theory. Before understanding molecular orbital theory, we should understand the difference between valence bond theory and molecular orbital theory. So in order to understand valence bond theory, we are taking an example: hybridization of CH4 molecule. Hybridization is a part of valence bond theory. So when CH4 molecule is participating in hybridization, basically the carbon atom in its ground state has the following configuration: 1s2, 2s2, 2p2, where there are two unpaired electrons in the ground state of carbon atom, but carbon has to make 4 sigma bond. That's why it will go in excited state. So electron from 2s orbital will go to 2p orbital. Now it has 4 unpaired electron. So before formation of CH4 molecule, this carbon atom undergo hybridization, means there is intermixing of pure atomic orbital of carbon to form hybrid orbital. So 1 2s orbital and 3 2p orbital of carbon will intermix and they will form 4 sp3 hybrid orbital. In this diagram, they have shown the 4 pure atomic orbital of carbon before hybridization. So after hybridization, these 4 atomic orbitals will intermix and they will form 4 sp3 hybrid orbitals. And these hybrid orbitals will orient such that there is minimum repulsion between them, and that is possible when the angle between them is 109 degree 28 minutes. So in CH4 molecule, there is 4 hybrid orbital of carbon at an angle of 109 degree 28 minutes, and there is an overlapping between hybrid orbital of carbon with pure atomic orbital of hydrogen to form CH4 molecule. There is mixing of pure atomic orbitals of same atom, that is carbon atom, to form the hybrid orbital. This point is important because when we are going to discuss molecular orbital theory, in case of molecular orbital theory, there is linear combination of atomic orbitals of the two atoms which is participating in bonding. Like if hydrogen molecule is forming, then there is a linear combination of 1s orbital of one hydrogen atom and 1s orbital of another hydrogen atom, and because of that there is formation of two molecular orbital. But here the same atom is giving its atomic orbital for intermixing in order to form hybrid orbitals. There are certain weaknesses in valence bond theory. Valence bond theory cannot explain the paramagnetic behavior of dioxygen molecule. So according to valence bond theory, this is the structure of oxygen molecule, and in this structure all the electrons are paired, either they are existing in the form of lone pair and bond pair. So according to valence bond theory, this should be diamagnetic, but from experiment we come to know that oxygen molecule is paramagnetic in nature. So that cannot be explained by valence bond theory. That's why we need another theory which is known as molecular orbital theory. So there are certain points in molecular orbital theory we are going through one by one. The first point is, in molecular orbital theory, the valency electrons are considered to be associated with all the nuclei of a molecule. Like if I am saying that hydrogen molecule is formed by 2 hydrogen atoms, so 1s electron of one hydrogen atom and 2s electron of another hydrogen atom. So there are two electrons in this hydrogen molecule. So these two electrons will move under the guidance of the nuclei of two hydrogen atoms. The second point is the atomic orbitals from different atoms combine to form a molecular orbital. There is linear combination of atomic orbitals to form molecular orbital. What is the meaning of linear combination? We can understand here that there is an atom A and there is another atom B, and one atomic orbital of this atom is psi A, another atomic orbital of B atom is psi B. When this psi A and psi B, these atomic orbitals undergo linear combination, the resultant is represented as this form. So this is linear combination of atomic orbitals. Like if I am saying that 1s orbital of one hydrogen atom and 1s orbital and of another hydrogen atom undergo linear combination, then there is formation of two molecular orbitals, bonding molecular orbital and anti-bonding molecular orbital. The fourth point is the number of atomic orbitals combined is equal to the number of molecular orbitals formed. And the fifth point is before the discussion of formation of molecular orbitals, we should know positive and negative signs used in wave function. So these signs are representing charge or these signs are representing phase. We have to understand that if the wave is in same phase, it has same sign. If the wave is in opposite phase, it has opposite sign. So these signs are used to represent the phase of a wave. For example, there is a formation of two molecular orbitals with the help of atomic orbital. So there is head-on collision of two pure atomic orbital. So here this is 2pz atomic orbital of an atom, and this 2pz atomic orbital is going to combine with another 2pz atomic orbital of another atom. So these two atomic orbitals are of two different atoms. When they are combining and if they are having the same charge, the lobes which are going to overlap, if these lobes having same charge, like here both are positive, then we'll say that this is constructive interference or there is formation of bonding molecular orbital. Similarly, when we are saying that these two atomic orbitals of two different atoms are overlapping such that they are in opposite phase, like here the lobes which are going to overlap, one lobe is positively charged and the other lobe is negatively charged, then anti-bonding molecular orbital will form. So the number of molecular orbitals formed is equal to the number of atomic orbitals combined. In order to understand linear combination of atomic orbitals to form bonding and anti-bonding molecular orbital, and bonding molecular under certain conditions will be G-rayed and anti-bonding under certain condition will be un-G-rayed and vice versa. If we want to understand that, first we have to understand the sign of a wave function. So we are going to study atomic orbitals of single electron system. Like 1s orbital or suborbit is spherically symmetric and it is independent of theta and phi. So what is the meaning of spherically symmetric? So here we have the complete wave function, and here you can see that in a complete wave function there are two parts, one is angular, the other is radial, and we are interested here in angular part. So in case of 1s orbital, the angular part is a constant, it is independent of theta and phi. For 1s orbital we can say that principal quantum number is 1, azimuthal quantum number is 0 and magnetic quantum number is 0. Similarly, if we want to understand about 2px, 2py, 2pz orbitals, that how the lobe is positively charged and negatively charged, we know that s orbital is spherically symmetric but p orbital is unsymmetric. So what is the meaning of symmetric and unsymmetric? Like here when we are talking about this 1s orbital and we have assigned a charge plus, it means that if we move throughout this whole orbital, its sign will remain same. It is symmetric everywhere, the sign will be same, right? If one side of a lobe it has positive charge and in other side it has negative charge, then we can say it is unsymmetric. But if we move from one point to another point across the nucleus, then the sign will be same in 1s orbital. Then we'll say that 1s orbital is spherically symmetric. Same way this charge can be positive or negative. Suppose in this atomic orbital, 1s atomic orbital, we assign a negative charge. Again, it means that if we move anywhere across the nucleus at two opposite ends, the sign will remain same. Anywhere the sign of the wave will be negative only. So we'll say that s orbital is spherically symmetric. Let us understand about 2px, 2py and 2pz. So we are starting with 2px orbital. This is the complete wave function. So angular and radial both parts are there. For 2px atomic orbital wave function, this is the angular part. So angular part is directly proportional to sine theta and cos phi. For 2px, the principal quantum number is 2, azimuthal quantum number is 1 and magnetic quantum number may be plus or minus 1. So before understanding that how angular wave function is going to depend on theta and phi, first we have to understand that what is the meaning of theta and phi, right? What is the meaning of theta and phi? So in order to understand theta and phi, we can say that suppose this is the Cartesian coordinate system or polar coordinate system, and this point is representing the position of electron from the nucleus. The nucleus is at origin, and this is known as position vector. So when we are talking about theta, theta is the angle formed by the position vector from the z-axis, and we can see that if this is the z-axis and we are talking about the angle theta, so the value of angle theta will vary from 0 to pi only. Either I am moving in this direction, or if I am moving from here along z-axis, if I am moving in this direction also, this angle will be only varying from 0 to pi. So the range of theta should vary from 0 to pi. We should understand this point. Suppose if I am saying that this is z-axis, and when we are finding theta, this theta angle is in all direction. It is forming a cone in all directions, right? So this cone is forming a theta from the z-axis. So this maximum variation of this theta is from 0 to pi. Similarly, when we are talking about phi, when we take projection of this position of electron on xy plane, this is the projection vector. So phi is the angle formed by this projection vector with the x-axis. So since this phi is in xy plane, it is in xy plane, so this value of phi can vary from 0 to 2 pi. So the range of phi is from 0 to 2 pi, while the range of theta is from 0 to pi. Now for this 2px orbital, we should understand that this is the diagram of 2px orbital, and this is x direction, and this is the nucleus. From nucleus there is a plane which is a nodal plane, right? There is a plane passing through the nucleus, and that nodal plane can be written as YZ plane. We are interested that how this lobe is positive and how the sign of this lobe is going to be decided, and that is going to depend on angular wave function. So this angular wave function depends on two things, sine theta and cos phi. So if we draw a graph of sine theta versus theta, and we know that the value of theta will lie from 0 to pi, and the value of sine theta, when the value of theta lying from 0 to pi is positive, this whole thing is positive. So we can say that throughout this sine theta will be positive. So sine theta is not deciding the sign of angular wave function, because it is always positive in the range from theta varying from 0 to pi. But let us see about cos phi. So if we draw the graph of cos phi versus phi, this is phi and this is cos phi, and we know that the value of phi will lie from 0 to 2 pi. So this is the diagram of cos phi versus phi graph. So we can see here that in the first quadrant from 0 to pi by 2, this is positive. In the second and third quadrant it is negative, pi by 2 to pi, and the third quadrant is pi to 3 pi by 2, and the fourth quadrant is again positive. So we can say that cos phi is negative in second and third quadrant, cos phi is positive in first and fourth quadrant. So now we can see that how we can decide the charge. So suppose here we are discussing, this is x-axis, this is y-axis, and we can say that this is quadrant number 1, this will be quadrant number 2, this will be quadrant number 3, and this will be quadrant number 4. So we are moving from x to y. So these are the quadrants. So we have find out that sin theta will not decide the sign because it is always positive, but the value of cos phi is positive in the first quadrant and fourth quadrant. That's why this lobe is positive. And the value of cos phi will be negative in second and third quadrant. That's why this lobe is negative in sign. So the sign of positive and negative lobe is decided by the angular wave function. So I hope that you are able to understand that why this lobe is positively charged and why the other lobe behind it is negatively charged. And because of this, p orbital is unsymmetric, because if we move throughout the nucleus from one lobe to another lobe, the wave will change its sign. So it is unsymmetric. If it has same sign, then it is symmetric. So let us again practice with another orbital, 2py orbital. This is the complete wave function for 2py orbital. It has radial as well as angular. We are interested in angular part, and angular part of 2py is directly proportional to sin theta sin phi. For 2py also we know that the principal quantum number will be 2, azimuthal quantum number will be 1, and magnetic quantum number may be plus minus 1. So this is the diagram of 2py. This is y axis and this is x axis, and we can draw from nucleus there is a plane. This plane is known as nodal plane. So for 2py the nodal plane is xz plane. So we know that nodal plane is a plane where probability of finding electron is 0. It is passing through the nucleus. The angular wave function is sin theta sin phi. Now we are interested in angular wave function, right? So the same way we are saying that the value of theta and phi, theta will lies between 0 to pi and phi will lies between 0 to 2 pi. So now we are interested in the value of sin theta. So we can say that the value of sin theta will be positive in 0 to pi, means sin theta is not deciding that the charge will be positive or negative, because throughout the range it is positive. So we are interested in sin phi. Again, if we see the nature, the graph of sin phi is similar, right? So here between 0 to pi sin phi is positive. In first and second quadrant it is positive, and in third and fourth quadrant it is negative. So if we see again the graph of 2py, we have taken this as the first quadrant, then we are moving in this direction. So this is x axis and we are moving from x to y. So this is first quadrant, this is second quadrant, third quadrant and fourth quadrant. So we can see that in the first and second quadrant sin phi is positive. So in first quadrant sin phi is positive, in second quadrant sin phi is positive. Between 0 to pi it is positive, and between pi to 2 pi it is negative. So in third and fourth quadrant it is negative. So that's why we are saying that right hand side lobe is positive and the left hand side is negative, and when we pass through origin on two different lobes the sign is changing. Because of that we are saying that 2py orbital is unsymmetric. Similarly, we'll try to understand about 2pz atomic orbital. So again this is the complete wave function. So the angular part of that is directly proportional to cos theta, and the principal quantum number for 2pz is 2, azimuthal is 1, and magnetic quantum number is 0. So this is the diagram of 2pz atomic orbital, and this is z axis, and we are interested in this angle theta, and the value of will vary from 0 to pi. So we can understand that this whole lobe is like a cone, right? And the angle here is 45 degrees. So we are discussing a cone like this. So from z axis, this whole thing at the surface of the cone, the angle in all directions will be 45 degree. So cos theta graph is here. On y axis this is cos theta, on x axis this is the value of theta, and we know that between 0 to pi by 2 cos theta will be positive, and between pi by 2 to pi cos theta is negative. Between pi to 3 pi by 2 again it will be negative, but we are interested in 0 to pi, right? So first and second, from 0 to pi by 2 and pi by 2 to pi. So if we see here that in the upper lobe where we have mentioned positive sign, Why the positive sign is there? Because when we are moving, the value of theta till here is 45 degree. The value of theta is 45 degree. Till here it is 45 degree only. So if cos 45 degree means cos theta will be positive. So that's why this sign is positive. And we are talking about the whole theta. It is not only in this direction. In any direction, if I draw a cone till here, this angle will remain same, right? So because of that, this whole upper lobe is positive. And when we are discussing about the lower lobe, we can see here that in the lower lobe, the angle lies between 3 pi by 4. This angle, if you count this angle, if you count this angle from this z axis, this angle, so this angle will be 3 pi by 4, 3 by pi by 4 to pi. So between 3 pi by 4 to pi, you can see here that this is the angle we are discussing somewhere here. So cos phi is negative, and because of that, this whole lower lobe is negative. So the negative sign of lower lobe is again decided by cos theta, which is angular part of the wave function. So I have tried my best to tell you that why we are taking positive and negative sign, and these signs are important in constructive and destructive overlapping of atomic orbitals. So in the next class, we are going to apply these concepts. So hope this video is useful to you. If this is correct, please like, subscribe and share for the second episode of molecular orbital theory. Thank you.